Yes, good morning, everyone. So, we're going to look at our project is aimed about object detection in crowded scenes. Uh, yes, so okay, it's Stephen, Elijah, and the title of our paper is titled Unraveling Crowd Complexity Enhanced Object Detection through Mask RCNN in Overlapping Scenes. So, we shall see why are we calling this that. Yes, so we're going to start by introducing object detection in crowded scenes. Like, why is this an issue? Is it even an issue? First of all, so why are we doing object detection? First of all, remember, object detection is a pivotal component in computer vision because if you don't detect anything, how are you going to tell that this is an apple that is different from an apple? This is a baby that is different from an old person. So yes, in the end we have to do object detection. So for crowded scenes, remember we're taking into consideration of every object. Every object, every noticeable, I would say thing in an image. So for example, if you look at our first image here, you will see a zebra crossing. So this should be, the algorithm should be able to tell that this is a zebra crossing and these are the different people within it and other things. So why is object detection in crowded scenes a challenge? Remember, during object detection, you're looking out for a single person, I would say, or a single object. But during in crowded scenes, you may have overlapping items or overlapping objects. So, for example, if you look at the second image that is close to testing, you can see that you can't even see some individuals, but yet they are there. So, meaning they are overlapped. Then we have another challenge, occlusions, then another one of classification and localization. So why is crowded scenes a challenge? So object detection, remember, uses identifies a single entity, like I said, but in a crowded scene, if the algorithms are going to find an issue with identifying if this is a single entity or this is if an object is a single entity or that object, given that the overlapping or occlusions is wrapped into a single entity, so which is going to cause an issue. So over the years, many people have used convolution neural networks as object detection in computer vision, stroke deep learning. Yes, but the issue with the convolution network, why we didn't go for it, because it leads to missed or incorrect detections. So, and why are missed detections an issue? Remember, we're dealing with a crowd, and crowd could be as a result of social events, as a result of traffic monitoring, as a result of surveillance. So, if you inaccurately detect someone or an object, it could compromise the public safety of during surveillance or even during any social event, say a concert. Then our model is mask RCNN. Because you've seen we have transitioned from the convolution neural network to mask RCNN. But remember, mask RCNN is also in a series of algorithms that came after CNN. For example, we have fast CNN, faster CNN. We have different algorithms that came through that. But mask RCNN outperforms all those models that I've kind of listed down. So why have we chosen that? It introduces a two-stage approach for higher precision by first proposing regions, then classifies them with rich maps for accurate detection, as we can see in the image attached. Yes. So our dataset overview, we chose the crowd human dataset of that dataset. And why did we choose this? Because it has real world complexity. By complexity, I mean it has the different images. So it has about it is divided into three sets. We have a training set that is composes of 15,000 images. We have a validation set of 4,370 images, as well as a training set of 5,000 images. So in total, probably these are like 1900, or I would say, or 20. No, sorry, 15,000, 15. So in total, this could be like 20,000 images, which are real world images. Then this dataset comes as well with annotations that include full body, visible body, and head bounding boxes. And these allow precise object detection and pose estimation. So every image, this was a sample image from the dataset. So every image has an image ID. It has the annotations, and the annotations come with the image ID, the different full body, visible body, and head bounding boxes captions or details, I would say. Then we did an exploratory data analysis. So the first graph is distribution of object counts per image, which displays a decreasing frequency as the number of objects in an image increase. And this indicates that images with fewer detected individuals are more common in the dataset. Then the second graph or below it is a distribution of whole body box width, which reveals a right skewed distribution, and this indicates that most of the individuals occupy a smaller proportion of the image width. So they occupy a smaller width option. Then we have a data pre-processing steps. We took two steps: normalization and rescaling. So then normalization normalizes pixel values to 0 and 1. Why we did that? Because it's a common practice and it standardizes the input data and often leads to faster convergence during model training. Then we rescale the images because of the varying dimensions of images. We give the images a uniform size of 124 and 124 pixels. Why did we do this? Because we want to promote efficient training. Then during our model training, so we're able to convert the annotations from the cloud image dataset to organized data, which is JSON data. Initially, it had come as an ODGT file, right? Then remember, for mask RCNN for annotations, we use JSON format that has it should be an object with a single class, but this came with images that are divided into separate classes. So we had to put them in an object within a single class. And then the training challenges we faced is despite the EDA and normalization, we weren't able to proceed from passing our annotations to developing our model, given the challenges of the complexity of the model RCNN, because of wanted to use the Matterplot GitHub repository. We cloned it, but it had an issue. So, and we failed to get out another well-maintained repository. That's where we got challenged. But in future, we want to give this a try and see what really happens out of curiosity. Other than that, thank you.